This is TechSNAP, episode 388. Hello and welcome to TechSNAP, Jupiter Broadcasting's weekly systems, network, and administration podcast. My name is Wes, and joining me this week is the man himself, that preacher of plasma, Mr. Chris Fisher. Hello, Chris.
Hello, Mr. Payne. I like that preacher of plasma. I might run with that. That's pretty good. You know, it's perfect, too, because we're having a pre-show plasma chat. I really am the worst, aren't I?
You sure are.
It's good to be back. I was away last week.
That's right. You've been visiting our BSD brethren down at Meet BSD.
Yeah, our BSD buddies. I got to hang out with Alan Jude, and I hang out with Benedict and producer Q5Sys, and a bunch of the folks from IX Systems, and some of the BSD royalty as well. It was pretty great.
Ooh la la.
It was pretty great. I'm going to do a review in the next Linux Unplugged with pictures and a blog post and all of it. I'm going all out. It was great. And you know, when we're down there, they're nice about it, but they're always kind of giving me a hard time for using Linux. And there's a couple of go-tos like pfSense and FreeNAS that they're really proud of. And some of the fundamental technologies that power things like pfSense are the cornerstones of what make BSD great networking operating systems. But it's not just for the BSDs, is it?
No, it is not. You know, while you were off in the BSD world, some things of note have been happening in the Linux world. I thought we could get you back immersed before we have to do another Unplugged. You can, refamiliarize yourself.
Right. Get my feet on the ground again.
Yeah, exactly.
So we've heard a lot about BPF. And on the Linux side of the camp, we've heard about eBPF.
Really, it's becoming a hot topic, and that's because, well, it's connected to everything. You can tell it matters because, well, Linus just came back. He'd been away, and of course, everyone's curious about all of the code of conduct drama, his feelings about it. He just wants to talk about the tech, and he got quoted recently talking about BPF. BPF has actually been really useful. And the real power of it is how it allows people to do specialized code that isn't enabled until it's asked for. Things like tracing and statistics or network filters. These are all great examples where you want to do localized thing that makes sense for one workload or one machine. Those aren't the everybody wants the same thing sort of tool that you might add to a big general kernel. This allows users to easily craft those just by themselves.
Well, now hang on here, Wes, because I thought BPF stood for the Berkeley Packet Filter, and it was essentially firewall software, not kernel software that can do all these other things.
And it did start out that way. Linux has an extended BPF implementation that's actually been put into a lot more uses.
Ah, hence the eBPF.
Exactly.
Okay, I can see why Linus is talking about this then. And he's not the only one.
No, Jonathan Corbett of LWN fame recently gave a talk at the Open Source Summit in Europe, and he made some pretty good points about why eBPF is important and why it's going to become more important really just all the time. And he put it well in that he thinks it's one area where people really don't understand how fundamental of a shift this is and all the technology it's enabling within the kernel. It's used all over the place. It's used for making security policy decisions. One example is seccomp BPF, where you can set up a BPF-based filter to disallow certain syscalls to be run from a program. It's used all the time for things like securing containers.
So BPF inside the Linux kernel is being used to do what exactly? It's making policy decisions? How does this happen?
Yeah, that's right. I mean, it can do a lot more too. It can be used to implement new protocols for things like IR remotes.
No.
It can use for instrumentation, things like DTrace level functionality for tracing things happening in the kernel.
Really?
It's also being used to make BP filter, which is an iptables drop-in replacement that's all the functionality of iptables replaced with, you've guessed it, BPF.
Now, that seems like the one thing I would expect it to do.
Yes, right. It, of course, has a networking heritage, and we'll get into that more in a second. But as you can see, it does a lot of other things.
Yeah.
Really, there's two things it's been doing. One, BPF is being used to supplement existing kernel functionality, but dynamically. So at runtime, without having to make a kernel module, without having to recompile the kernel, the user can craft custom BPF bytecode and then get it first verified. There's some sanitization that happens. The kernel does checks to make sure it's not going to break the kernel, but then it gets loaded and run from kernel space. So this lets users dynamically extend the kernel without having to wait for kernel developers to do it for them.
So the eBPF system is essentially in part, a virtual machine that lives inside the Linux kernel that accepts bytecode to do things that the Linux kernel doesn't normally do.
Yeah, exactly.
And it's not the only VM in the Linux kernel, so that might surprise some people. What, an entire VM inside the kernel? Yeah, that's not the first, it's not the only, but it is extremely powerful.
It's both simple and powerful. It's not Turing complete, so it can't do arbitrary computation, but they've hit a really nice balance where it turns out it can do pretty much all the useful tasks we need it to do, and it's surprisingly small,
and
elegant,
fast, I assume.
And fast. At least with some of the nice just-in-time compilation techniques that we have in the kernel, it is pretty fast.
Do I have to know bytecode to take advantage of this BPF
Thankfully
system?
not. The tooling is a pretty actively evolving world, but we'll talk about that, and there's some new tooling that's just been released that should make things a whole lot easier.
Cool. Well, maybe you can clear something up for me, Wes, because I've also been led to believe that eBPF in the system, in a sense, can be used to kind of push code out of the kernel, back into user space.
Yeah, that's right. It's not always intuitive, but there are some examples, things like the express data path, where you make eBPF programs that run on the kernel, but then filter data out of the kernel. So those programs are allowed to touch the kernel data because they can be sanitized and verified. And then they export that into some sort of shared buffer, shared memory that user space can access too. So with Express Data Path, that's a way for you to skip a whole bunch of the network stack and really do really fast network processing for things like, let's say, preventing a DDoS attack, which you can do in user space much faster than a generic kernel TCP stack.
Okay, you just got back to networking again there. There's obviously a strong networking heritage with BPF. I mentioned pfSense at the top of the show. That's what powers the pfSense firewall that the MeetBSD crowd was so proud of. How do we go from something that was designed to filter packets to something that's part of a virtual machine in the Linux kernel? What's the history here?
Well, you're right. It does start with filtering packets. And, really ever since people started having networks, you wanted to see what was going on those networks. You need to be able to make decisions about packets, and you just wanted to be able to inspect packets. So this all starts off with various operating systems in the dark old days of Unix when they developed different APIs for packet sniffing. So a lot of them just weren't that great, and many of them involved making whole copies of packets into user space, which was really expensive.
Time intensive.
Yeah, exactly. This all changed in 1993 with a paper titled The BSD Packet Filter, hence the name BPF. This was by Stephen McCann and Van Jacobson. It's just 11 pages long. It's actually pretty simple. So if you're interested in this sort of stuff, it's definitely well worth a read. There'll be a link in the show notes.
TechSNAP.systems/388.
And if you've used the popular TCP dump tool, which I know you have, TechSNAP listener, well, you're using BPF under the hood.
You mean I've been BPFing all along and I never knew it?
Yeah, that's right. So TCP dump actually works in basically 3 parts. First, you have an expression parser. So you type something into TCP dump to tell it what you want to do. So I want to look at IP packets, UDP, actually, port 53. So maybe you're trying to just look at all DNS requests. It's an easy thing to do on a Linux system. The result of that, after it all gets parsed and emitted, is a special minimal bytecode, the BPF bytecode. And that's the instruction set, are particular sequences of instructions that run on the embedded BPF VM. Now, once you have your compiled BPF bytecode, you attach it to the network tap interface. So it actually gets attached onto the network interface. And that means every time you get a packet through that interface, or a frame, or whatever layer you're working on, that BPF code is triggered. It runs and then determines the result of either accept and filter this packet or let the packet keep flowing through.
Let me see if I'm tracking you correctly. At the kernel level, it is sending the network traffic through the BPF virtual machine, and then in there, the bytecode, which I would imagine is simple but gives it some sort of decision instruction set to work off of. It makes its decision, and then it returns results back to TCP dump?
Yes, exactly. And one of the things about BPF is that it is surprisingly simple and concise. One quote about it from the paper is, it consists of an accumulator, an index register, a scratch memory store, an implicit program counter. And that's about it. It's a pretty simple little virtual machine, but it's enough that you can write a program to sort of look like, go grab the header, go see what port it's at, go inspect these properties, and make a decision. Now, there are some rules about what you can and can't do. You can't do things like loops. There's a whole bunch of just simple restrictions that make it easy to do static analysis and actually improve that For instance, the program will actually halt, that it won't make a loop forever inside the kernel,
So you don't have a persistent application running inside the kernel. You can't put like an Nginx web server in there.
Yes, exactly. And that's a good thing. And it kind of speaks to the heritage of BPF. When the paper was published in 93, it had actually already been in use for 2 years before that. So it's been production ready for a long time now. Now, of course, the eBPF is a little bit different, and we'll get into that. But the general idea, the basic virtual machine, it's battle tested.
Okay, so that's the history of BPF, but now we're talking today, 2018, as we record this. What's the E now in eBPF? What makes it extended?
That is a great question. We actually haven't had extended BPF in the Linux kernel for all that long. It first showed up in version 3.18, released in December 2014. Now, what eBPF offers is an in-kernel virtual machine much like BPF, with a few crucial improvements. First, eBPF is more efficient than the original BPF virtual machine, mostly thanks to its just-in-time compilation of the eBPF code. So it takes eBPF bytecode and then converts it right there to actual native machine code. So, x86, whatever architecture you're on, it doesn't work for, I don't think it works for all the kernel architectures, but most of them you get that really efficient pre-compiled code. Secondly, and importantly, it's designed for general event processing within the kernel. So it's not just focused on network anymore. By being more general, it allows kernel developers to integrate eBPF into kernel components all over the kernel, and that's why you see it deployed so widely today. And finally, it includes efficient global data stores. Now, eBPF calls these maps because the first one implemented was a map sort of data structure, key value. There's also arrays and a number of different data structures you can use. These let eBPF programs keep state, so you can start doing things like aggregating data, making statistics, drawing nice histograms for your users, and you can interact with user space. So you can set up shared memory buffers. You can allow user space to modify running eBPF programs. So if you have a couple different paths and you want user space to be able to control that, now you can.
So eBPF extends way beyond networking, and you can use it to measure and track many things and make certain policy decisions. And I've noticed that the Linux community often refers to it as just BPF. So in the context of Linux, you have to sort of make your own translation in your head and realize they're talking about eBPF.
Yes, exactly. That is what we're talking about. In official documentation, it should say eBPF. But when people are being colloquial or just, giving a talk, you'll hear BPF.
I asked you earlier in the show, and I'm still curious, how do you feed the eBPF monster? How do you write for this virtual machine? Because it sounds like I have to be a bytecode expert.
That is one option. If you really hate yourself, you could just start writing raw bytecode. And in some cases, maybe you have to if you're really specialized use cases. But the most common way to do this is, actually LLVM, the compiler toolchain, has an output for eBPF bytecode.
Really?
Yeah.
They've built-in support for eBPF?
They sure have. So you can write a C program, compile it with LLVM, and then have that spit out eBPF bytecode, which then actually just resides in a normal ELF file.
Okay, so you still have to know how to write C. So we're talking, this is a tool for advanced types of workloads and advanced users that know what they're doing.
Yeah, in this form, it's not necessarily readily accessible. It would be more of a tool set that you might use to craft higher level programs. But that's the raw interface for starting to get that. So you could write some machinery around that generating procedure, maybe need to customize it, and then eventually spit out the customized bytecode that you would actually go use.
You could see companies that are doing very specialized types of tracing or diagnostics for really high-end workloads like AWS engineers, or developers like the author of TCP dump, who's writing for this virtual machine.
Yes, exactly. And there are some other tooling that's now available. We'll talk about that's a little bit higher level and easier to use. Regardless of how you make it, once you have your eBPF program, you need to load it into the kernel. This is done with the special BPF system call in Linux. Basically, the system call allows for the bytecode to be loaded along with a declaration of what sort of eBPF program it is, because we now allow these programs to be attached to different sorts of devices and objects within the kernel. You have to sort of specify, because it's different if you're saying attach this to a network socket or attach this to my program over here.
Sure.
There are a ton of different types as well. So socket filters, kprobe handler, traffic control schedulers, traffic control actions, trace points, the express data path that we mentioned, performance monitors, C groups, all kinds of stuff. And finally, once you've got it loaded, you attach it to the system that you're actually targeting. And again, there are different types of eBPF programs that you can write that target different sorts of systems. So this is all a little bit specific depending on what you're doing. You set things up, you basically tell it like, all right, attach to this PID or attach to this socket. Once it's active, it starts filtering, and the kernel starts handing off data to the eBPF programs and executing it, either interpreting it on the virtual machine or doing its just-in-time compilation and shipping it off to the real processor.
It is staggering how much can happen in real time inside the Linux kernel, moving data between different subsystems in what happens so fast, it might as well be instantaneously practically.
Yeah, and actually that's a really big deal here is traditionally you would probably have to make some sort of context switch here because, you couldn't customize the kernel code, so you had to go fork out to user space.
Right.
That's really slow. When you do this and you get, really nice just-in-time compiled bytecode ready to run, well, you skip a whole lot of performance loss. And that means you can actually do some high-performance networking tasks. You can spin up thousands of containers on a tiny virtual machine. It's all amazing.
Listening to all of this, I'll tell you what piques my interest is the future a little bit. 4 years isn't really a long time in the overall scheme of enterprise technology, especially when you look at how some systems take forever to get updated and creating products around technologies can have lead times of years. It has me kind of curious about what the world might look down the road when eBPF has been baked into the Linux kernel for a decade.
You say that, but you're totally right. We only got eBPF in RHEL in the 7.6 release.
That's not that long ago.
No, it is not. Really, though, I think there's a huge future. A lot of that's because eBPF is well constructed. It's restrictive, and it's really simple. It's also highly portable, which we'll see that's important. And it kind of forced us to change how we solved a lot of problems and how we thought about things. It removed objects and a lot of stateful, like if you imagine like a custom TCP stack that's implemented in the kernel, there's a lot of stateful code there handling a lot of different objects. BPF, it's just functions and efficient data structures to store state. So you can shrink the design, you can make really simple bespoke programs that can be run, and it's compatible with just about any kind of program design that you need to do. So synchronously, asynchronously, parallel, distributed across all kinds of cores or just running on one core. It's flexible, and that means we're just going to keep seeing more use cases. And I think that's why we see so many use cases already.
Yeah, definitely. And a bit of an ecosystem is brewing around eBPF as well.
Oh, yes, that's true. We talked about XTP, the Express Data Path. That's one example I like because, well, there was already all of these user space networking things like DPDK. And those just kind of talk to the NIC. You have a special driver so that the NIC hands off packets right to this user space implementation that's all custom code. You compile it down so that you just get a very efficient, minimal, only the functions you need. XTP is the kernel's chance to play in that space. And they're saying, like, you don't need to use this third-party framework. You can set up a BPF program to grab your packets out of the kernel. We'll ship them to user space just as fast. And in this modern era of so-called smart NICs, that's a NIC that has additional meaty processors right on the chip.
Mm-hmm.
Because BPF bytecode is portable, right? It has this abstract virtual machine sort of implementation. You can ship your BPF code to the NIC. And so instead of running it on your CPU, the NIC will run your BPF program and decide when to ship those packets to you. But it's the same program.
So you can get probably massive scale with that.
You sure can.
And we're back at networking again, Wes. It's funny how it keeps coming back to that. No surprise there, really. You mentioned earlier, though, and I wanted to clarify on this, it sounds like there is an effort underway to potentially replace iptables with BPF.
Yeah, that's right. Back in the spring, we talked about this a little bit, I think on Linux Unplugged. It's called BP filter. And the idea is it will be almost a drop-in replacement to replace the long-standing in-kernel functionality for this, you know it, our friend iptables. Now, iptables has been kind of a blessing and a curse. It is very flexible. You can do all kinds of stuff. You can almost always figure out a way to hack through, come up with some kind of iptables rule that will get you out of a situation you're in. But also, I'm sure you've dealt with this, you inherit a box, you come to find 5,000 different iptables rules in all kinds of different chains, and you're trying to figure out, like, what's happening and how do I maintain any of this? The other big problem is, well, iptables was designed when we were all still on dial-up. That is not the world we live in. If you're let's say, Cloudflare, trying to, serve giant CDNs for your customers, you operate on whole different kinds of scale. You just can't have linear rule-based processing, and that's how iptables fundamentally works.
Right, it goes through each line.
Yeah, exactly. Now, there has been some sort of workarounds, things like ipset, which allows compressing a bunch of rules to work on multiple IP addresses, things like that, but it's just not good enough. An example that struck me is kube proxy, and that's a little proxy that handles all the networking routing requests for various containers when you're running Kubernetes. It installs iptable rules for each backend service that's being served to, right?
Right.
You can get in situations where you have 160,000 rules and it takes like 5 hours to install them all. That doesn't work for anyone's real production workload.
No, that's not good. That's not good, Wes. So can eBPF, or as they call it, BPF, be our hero here?
Yeah, exactly. So now instead you take this new approach, and that's really what we're talking about here, is instead of having all of this custom code hard-coded in the kernel for doing these kind of network filtering that you then configure with this userland tool, the userland tool will then generate an eBPF program, right? It's kind of work just like TCP dump. It'll take the way that you interact with it, compile that down into some bytecode, ship it off to the kernel, and then instead of having this big, giant program that can do all kinds of arbitrary filtering, you make a custom program to just run the firewall code that you want. So there's possibilities that it can be a lot faster.
You really have my thought process running in all the ways this could be a useful tool. And you can tell that my MeetBSD experience is still fresh because they gave a whole presentation on how amazing DTrace is. And I got to tell you, it was a very impressive demonstration. And I heard you mention earlier that this could lead to essentially DTrace for Linux. Can you expand on that part of it? Because this is a tool I think everybody listening to this show could take advantage of.
Actually, it really is, in part due to the hard work of people like Brendan Gregg and a lot of the community that's around that's interested in tracing and observability. So Linux 4.9 added the final capability we needed, which was timed sampling. Now, for a long time, we've had what's known as BCC, or the BPF compiler collection, and it's a handy set of tooling. You get some low-level libraries that then have high-level hooks in either Lua or Python, and this lets you write some BPF programs that ultimately compile down to the bytecode, but you don't have to write C. You can write some higher-level tools. This still isn't DTrace easy, though, right? So DTrace is super handy because it's dynamic tracing. You don't have to have pre-instrumented your app. You don't have to pre-instrument your kernel or rely on static trace points that are pre-coded in your kernel. You can come along if you have DTrace installed, which, hey, it is by default on a lot of those Solaris type systems. You just go. You can start tracing stuff. You can write a one-liner right on the command line and get whatever you need.
Yeah.
What we have had in the BCC collection, though, is a lot of handy programs. People have crafted things like exec-snoop, which will just show you in real time as people are working on your system. You can just watch all the executions that are happening because you just load a BPF program in that filters all the syscalls that are happening and prints out just what you need to know. Another one that's really handy is just like looking at all the TCP open connections or like a TCP connect connection. You can see all of those. Those are printed in real time. So you can go get that installed. We'll have all the links and stuff. There's a whole bunch of handy utilities that you'll probably want to use they're already there. They have, nice little command line arguments. They have nice flags that you can use. They're just great observability tools. But they weren't quite DTrace. So it was really big news when on October 8th of this year, Brendan Gregg announced that with Alistair Robertson, BPF Trace has gone open source. And this is the closest thing that we've ever really seen because it is this. It's a new language that looks a lot like DTrace, implemented for BPF. It's a front end that's super user-friendly that lets you write one-liners in a powerful, expressive language to run tracing requests. It's fantastic.
And its official name is BPF Trace.
That's right.
This is pretty exciting. It looks like a really powerful tool that will use existing Linux kernel facilities like eBPF, like user probes, like trace points, like perf events, as well as the BCC libraries that Wes mentioned. And internally, BPF Trace uses the Lex parser to convert programs to AST. So this is interesting. So Lex is how you actually talk to it, and then it'll convert it to its language, which is AST. Do I grok that correctly?
It's a little deeper than that. The way it works basically is they've just used some handy tools to implement a parser for their custom language, and you can see some scripts here. They have comparison of what a modern BPF Trace version of some of Brendan Gregg's previous DTrace tooling was. So one example here is looking at seek size. It's seeksize.d is what it's called. There's some nuance to exactly what they're trying to find, but you can see it kind of looks a little bit like an awk script, sort of a C-ish looking language, but it has nice things like easy arrays and access to all the different trace points that you might want to find, and K-probes and U-probes, and everything really.
This is pretty nice. And BrandonGregg.com is where he has a blog where some of this is posted, including visuals to help with all of this. And like we've said a couple of times now, TechSNAP.system/388 will have links to all this stuff. So if you want to see some diagrams too to help visualize what we're talking about, you could find them there.
Yeah, there's great diagrams, and there's a whole bunch of documentation already available, which is fantastic, including a one-liners tutorial. And there's such fun stuff in there, like tracing all file opens across your system. In a one-liner, you can write right on the command line, or getting system call counts by process. Just right there. It's about half a line long.
Well, I do have to be honest with you. Listening to how powerful eBPF sounds, the fact that you're executing bytecode inside a virtual machine inside the Linux kernel, it does tingle my TechSNAP sense a little bit, and I do worry about the security implications of something like this inside the kernel. I can't help it, Wes.
That's a natural question, and I'm glad you asked, Chris, because, well, it's the real world. And even though, as I said, it's battle-tested, it's been around for a long time now, nothing's perfect. And so we have seen things back in 2017, for instance. There was a verifier bypass that had some nasty implications. Of course, that's all patched now. We also saw just this year with the Spectre vulnerabilities that there were a couple patches that landed in 4.15, fixing some variant 1 speculative execution bypasses, as well as some other stuff with just the interpreter for variant 2. So you can now just switch the interpreter off entirely and only have the compiled version.
So it wasn't in the virtual machine.
Yeah, there's a little bit of nuance there. There's also some settings you might want to use, like you can set it so that unprivileged users can't load arbitrary BPF programs, so you have to have root. That might be something reasonable to have on some of your production machines. So there are some considerations, but I think there's a good quote in one of Brendan Gregg's articles. All eyes are on Linux. And to add on top of that, there's this one implementation really that connects to a lot of kernel stuff. So the more kernel functionality we can rip out and replace with a more generic BPF-based abstraction, that solidifies things. That makes less code, simpler code that we can focus on. As long as we can just, instead of maintaining this big TCP stack, for instance, we can just maintain this virtual machine code. So not only are we minimizing the amount of code that we have to look after in the kernel, we're changing the way we view and interact with our system. So there's security concerns, yes, but there's also some security wins, having a simpler system that we can understand and have a lot of eyes on. And it kind of changes the way we think about what the kernel is and how it talks to user space. Right now, we think about it as like a hard kernel with a firm, known API boundary. That's all the sys calls. But now, with BPF programs, that's a new, more fluid way. And you have data being pushed out of the kernel. You have custom user programs being loaded into the kernel. You could almost say it's getting a little closer to a microkernel where you have a little a core kernel, and then you implement things not as modules but as BPF.
Thanks for going to TechSNAP.system/contact for sending in your questions and your feedback. We love getting those. Also, those war stories. Love reading those war stories. Love reading those war stories. We got a long time email in from Stefan, and he has a giveaway in here that was a clear indicator he's a long time listener. And so because of that, we are dedicating this episode to him. He writes, I'm a longtime listener of JB and wanted to thank you for all the valuable information you've given me over the years. So, what I would like to see somewhere in the future is a deep dive into eBPF and the BCC tools. He says, anyways, keep up the great work. Greetings from Austria, and then in parentheses, no, Chris, not Australia. Which right there is the giveaway that he clearly is a long time.
On Stefan.
In fact, I distinctly remember one time in one of my most embarrassing moments on air, I mixed those two up because I spot read. And what I do when I read is I spot read and I pattern match. And if I see A, U, and S, you're moving fast. You have to manage the mixer and all kinds of things, right? And on average, we get a lot more emails from Australia than we do Austria. So I think before Stefan's written into the show, and I think I said Australia in the past. So
But
I
you
apologize.
didn't this time.
No.
It's a team effort.
But I could tell that was it right there. That was the tell. He's a longtime listener. So, Stefan, thank you, and we dedicate this episode to you.
Speaking of longtime listeners from faraway places, we've got another message. Yusuf from Alexandria, Egypt. He writes, I thought older episodes would also be available through the new website. I was in a conversation with a couple coworkers yesterday, and I was trying to talk to them about the issue of either having a privileged user account or using sudo. And while I wanted to refer them to that question, I had asked that question to Alan years ago in TechSNAP episode 188, but I had to go digging through YouTube. He is nice to all of us that link is included. He sent that right along. Unfortunately, it took him a little while to find it.
Yeah, so this is a bee in our bonnet, as they say, but we're actually working to fix it. So to explain what's going on here, TechSNAP.systems doesn't have the entire back catalog. And that's because for so many years, many of the quote-unquote portable podcast clients, which are nothing really like what we use today. Like today, we have great podcast apps. But back in the day, when we first started the TechSNAP program, there was real size limits on how big the RSS feed file could be. And if that feed file would exceed, like, I don't know, it might have been 300K. I can't remember exactly. It was not a lot.
Well,
500
you load the whole thing in memory like a couple times, Chris. It's real. It's easy.
What we need is like an eBPF bytecode to parse the RSS. Oh, sorry. Anyways. And so what we would be forced to do, much to our traumatic experience, it was like this. It was like cutting off a limb. Like you'd have to go into this was bad, guys. You'd have to go into our RSS feed management application, and you'd have to just select part of the show's history, and you'd just have to delete it from the feed.
No.
I mean,
Say it ain't so.
Wes, it almost brings a tear to my eye just talking about it right now. And what happened is there was only a certain depth to the RSS feed. It only went back so far. And so when we moved to the new site, it pulled in all of the external resources to the new CDN via the RSS feed. And so if it wasn't in the feed, it didn't exist. Now we are going back manually by hand and recreating entries for the old episodes. However, that also first requires that we collect all of the old media from various different distribution CDNs that we've used over the years. And Mr. Payne over there is going to potentially concoct us some automation to blast the back catalog into our system eventually, once we've gotten to the point where we've got all the media collected and all that kind of stuff. But it is a process, Yusuf. And so thankfully, if you do dig around, you can find it because it's out there. But our own site is not one of those places if you go too far back into the back historical catalog of the TechSNAP program. But we are working on it. In fact, we're not just doing it for TechSNAP, we're trying to do it for all of our shows. Thank you, Stefan and Yusuf, for your longtime listenership and for writing in. We'd love to hear from all of you out there. TechSNAP.systems/contact questions, feedback, topics you'd like to hear us cover, corrections to my pronunciations, and your war stories. TechSNAP.systems/contact.
If you have your favorite of the BCC tools or favorite uses for eBPF, hey, let us know about those too.
That would be great.
Well, that'll bring us to the end of this episode of the TechSNAP program. But before we go, some final thoughts.
Yeah, we'd like to use this segment as a chance to share either a pontification of ours or a cool tool, maybe a link that we found during this week. And just before we recorded this segment, we were debating which one we wanted to go with. And it came down to only one solution, only one answer, because Wes was chatting away last night, obviously working away on a project. And you could see your line of thinking as, I'm looking for this thing. Hey, I think I found this thing. Hey, BSD Now talked about this thing. I did it. I love it. So let's talk about your tool this week, your plumbing solution.
That's right. It's Up, the Ultimate Plumber. And I was really sympathizing with Yusuf last night because I saw Up out there on the internet and I played with it. And it was really neat, but it reminded me of a tool I'd seen discussed on BSD Now way back when. Turns out 2014 is way back when.
Wow, good memory.
And it was painful to find. So it really instilled in me the belief of, we gotta tag those things really well and let Google Foo capture all that information.
Yeah, we are trying to get better about our tags, but we've always had tags to help with search, but it's only been within the last, I'd say, 10 months that we've gotten really clever about our tags.
So hopefully this is a problem we've solved proactively.
So the Ultimate Plumber is a tool for writing Linux pipes in a terminal-based UI interactively with instant live preview of what the command results would be.
Yeah, exactly. The main goal here is to help you interactively explore data. You know, when you're trying to build a pipeline or you have like, oh, you've got this new CSV that someone dumped on you, you're going to make multiple pipelines. You keep having to copy and paste or go up or look in your history. If you go check it out, they've got some good previews here. It just, as you type, it reruns your pipeline, re-renders, and displays. So it's kind of like having an interactive version of the watch command.
Yeah, this is pretty nice, really. And it's so fun to play with these pipes, too. It's when you switch to Linux, so you're coming from like a Windows admin world, and you switch over to Bash, and you start playing around with pipes, you go, oh, this is the best thing ever. Like, this is how it should work. But it's hard to really wrap your head around it. So until you get to that point, a tool like this can be super useful. Or for somebody like me, who just needs a little help every now and then.
This seems also like a great learning tool.
Yeah, absolutely.
People new to this stuff. Now, I should warn you, be careful. Don't, because it runs these things when you type, don't be typing RM, don't be typing DD. Those are just dangerous. They talk about that. There's a big discussion over on Hacker News about like, well, how do we make these things secure? What should this be like? But I think because pipelines are such a big part of how we use computers, these tools like PipeCut, which is the tool I was thinking of mentioned on BSD Now, they're going to be important as we build and have to maintain data workflows in pipelines.
Also, for any of you out in the audience who have experience with AWS, rumor has it that Linux Academy is hiring for their next AWS training architect. And if you've got some experience with AWS system, I would encourage you to apply for that position. I'll put a link in the show notes. I think it'll probably be the last link in the show notes at techsnap.systems/388. That position's open, and rumor has it they're motivated to fill it. So I wanted to put the word out. There's got to be somebody in our audience.
There's got to be.
And it's remote, too, I believe. That could be pretty nice.
It's a great way to leverage your knowledge, and you'll probably learn a whole bunch more. Thank you so much for tuning in to this week's episode.
And we'll see you back here next week.